And of course, this is specific to Fathom. We're going to be looking at the modules for Fathom. My name is Jeff Warren. I'm the Director of Sales here for Applied Flow Technology. I handle all of North America. And I'm glad to be here today. It's I shouldn't use the word exciting presentation because that's pretty far stretched, even for a sales guy to say. But the topic is good and the content is good, and really what we try to do here is we're going to keep it fairly technical in nature. With no further ado, let's move forward. The agenda for this morning is we're going to be talking about, well, really a number of different things. We're going to talk about the 3 modules, which of course is the goal, seek, and control. We abbreviate that as the GSC module. The XTS module, extended time simulation, and then the settling slurry module, which is the SSL module. Now, all of that somehow miraculously is going to take 30 to say 35 minutes. Then we'll talk about some of the key features, do some Q&A, and some closing comments. Now, you may be asking yourself, well, we're muted, how do we ask questions? And we're not muting you because we're not interested in what you have to say. We're muting you mostly because our audience is international, a bunch of different time zones, people all over the place, and a lot of people. That coupled with distractions kind of makes for a miserable webinar. And so really the way that we encourage people to ask questions is on the right-hand side of your screen with the GoToWebinar control panel. You'll see a field in here that says enter questions for the staff. And what you'd simply do is type those in. And so already I've gotten a couple questions, a couple comments, and what I'll do is periodically be checking those questions, and if it's appropriate at the time, I'll just bring them up to the entire audience. I'll read the question so everyone in the audience knows what we're talking about and then respond with hopefully an adequate answer. So let's keep moving on. The time allotment that we have is about 40 to 45 minutes. You know, in today's engineering community, people are pressed. Engineers are pressed to produce more now than ever before. And so that makes time pretty valuable. So we're going to keep this under 40 minutes. If I may, a very quick introduction. When I talk about quick, I mean in the order of less than 2 minutes of who we are. People often ask, who is Applied Flow Technology? Who is AFT? Well, our company was founded in 1993, so we're coming up on our 20-year anniversary. Products have been around a long time. Specifically, Fathom was introduced in April of '94. And so, you know, it's tried and true. It's tried and true in the sense that it's used globally by more industries than I care to list. And so if you do that for 20 years, you work out all the bugs, you add new features and new requirements. And so, you know, at this point we're on version Fathom 8, and it's very robust software package. Of course, we have the different modules associated with that as well. Our company is located in Colorado Springs, which is in Colorado here in the United States, and this is our office building here. You'll notice in the background some mountains, and I tell you, people will come here for training, they'll come here for meetings and what have you, and it's just a beautiful place to work. It's a beautiful place to live, and so when folks come out for training, usually we find ourselves going on hikes and climbs in the mountains just on some of the off time, and people really enjoy it quite a bit. Very brief overview of what we have to offer and our solutions that we have for the different regimes. Now, for incompressible flow, of course, we have Fathom, the 3 modules that we'll be looking at today. We also have Mercury, and I get this question a lot. The question is, what is it? Well, it's similar to Fathom, except that it's got an optimization engine on it, or included within it, that is very powerful. In short, it optimizes systems either for 2 things. The first is initial cost of new systems, or the second is energy cost, life cycle cost. And of course, in today's climate, with energy being such a focus of attention, and certainly the costs associated with that, Mercury is very successful because of those reasons. For compressible flow, we have solutions for that as well. We call it Aero version 4. We have a module that's attached to Aero, and that's the GSC module. We also have Titan. It's very similar to Mercury, except for it's for compressible flow. We also have solutions for water hammer. We have the Chempact property database and some utility software. All right, enough of that. It gives you the 3-minute overview of who we are and what we have to offer. Well, you came here today because you want to learn about the modules. Now, if you've been a bit of a student of AFT over time, you probably noticed that we used to have 5, and now we have 3. Well, what happened to the other 2 might come to mind. The first module that I'd like to talk about is the CST module. It's the cost module, and it's just that. It's a cost database. That way, when you're designing your systems, you know the costs associated with that. That's been included in version 8. It's no longer a module. The same is true for the NSL module. That is included in version 8. So for anyone out there that has version 8, those 2 modules are included as in the base package. Let's start out this morning by talking about the goal, seek, and control module. Let's talk about what it is and some of the advantages of using it. Quick intro. Well, in a short description, the GSC module automates the process of changing input variables to achieve the desired design goals. It's called goal seeking. Now, if you do this for one parameter, you know, the manual process, yeah, it takes some time, but you can do it successfully. The complexity comes into play when you start using 2 or more parameters at the same time. Now, if you try to do that manually or iteratively, it's very complicated. It's not an easy solution. There's too many what-ifs. The complexity is too great. You end up doing side calculations. Again, today's engineers are being more pressed than ever before for time and productivity. We don't have time to do iterative type of approaches. And so in this day and age, you would expect automation to be a bit of a focus. And so, you know, that's what the GSC module, that's where it really shines, is where you're able to, in essence, save time and iterations in the manual process, and you allow the software to find the solutions based on your goals. You can do either point type of goals or group goals. I'm going to show an example of this here in just a minute, where it's either groups of pipes or junctions that satisfies some type of operating criteria. Not only that, but we can also link some of the variables to force common solutions. I'll show you an example of that as well. Some of the interfaces, if you will, as far as defining variables. What does it look like when you enter the goal seeking control manager? Again, I'm going to show it to you, but let me first define it. When you take a look at the goal seeking control manager, you're going to get a dialog box that looks something like this. You'll have 3 different tabs. The first is variables, the second is goals, and the third is numerical control. When we're looking at specifically now the variable tab, certainly you can define a new variable. You can duplicate an existing variable. You can delete any variable, and you can delete all the variables. And if you read left to right, any of these variables, of course, I only have one listed here, but in this case, I'm going to apply it. The object type is a junction variable. In fact, it's a pump. It's J7, and we're going to vary the speed according to meet some type of a goal. Now, if I wanted to link this pump to, say, another pump, I could in the model. If I wanted additionally to put boundaries, whether it be lower or upper, I could do that as well. So people often ask, how many variables are there? Well, there's over 40. And I'm not going to read each and every one because it gets really boring really fast. But in short, you know, you can have different types of variables, whether it be for assigned flows or assigned pressures, branches, heat exchangers. As you'll note with a heat exchanger, you have a number of different variables associated with that. Well, the list continues, goes and talks about orifices, pumps, spray discharges, valves. A lot of our clients and customers, they'll use the GSC module to vary a valve, maybe its open percentage, based on some of their demand or some of their goal. And so instead of iteratively coming up with those solutions, now with the GSC module, you can have Fathom do it. Goals. Well, you define it the same way. It's the second tab over in the Goals Seek and Control Manager. And you can create goals as you did variables. Now, let's talk about the different types of goals. The goal type could be a group goal, it could be a point goal, or it could be a differential goal. There's three different types of goal types, if you will. Okay, I can certainly apply any of the goals that I have listed in the Goals and Control Manager. And again, it reads left to right, and in this case, if I took the top one, it's a group goal. It's a max min with a volumetric flow rate that's got to be greater than 400 gallons per minute for the discharge lines. So I'm going to show you a model here very quickly, but on how you would use this. I wanted to give you some definitions up front. Well, as we talked about, there's three different types of goals. Again, it's point, differential, and group goals. I'll give you an example of a couple of these here in just a second. There's over 150 different types of goals that can be applied to pipes, junctions, or groups of pipes and junctions. For example, if the object type is a pipe, you can have different goals associated with pressures, whether it be static maximum, or stagnation, or gradient, or even the drop in friction of the mass flow rate. Well, the list goes on, talks about area changes, assigned flows, branches, control valves, again, heat exchangers, pumps. A lot of times we'll have different set points where people will use VFDs to control a pump. Maybe it's based on downstream flow or pressure, and we'll want to be able to dictate or control the speed of the pump, and so we can, using this module, the GSC module, determine what the speed will be. Well, with no further ado, let's take a look at a model here. Let's take a look at the Freon system model, which I've already created. I can zoom in a little bit here so our viewers can see this okay. And really, a quick description, if I may, what we have is two different reservoirs. We're going to pump from J1. It's going to split from J3, where flow goes both ways, goes through two different heat exchangers, connects at a common point, and then goes off to J8. So fairly simple system. If I were to look at the system properties, we'll find that we're going to be using from the AFT standard database, we're going to be using refrigerant 11. It's a liquid, and it's at -50. So we're going to start out at J1, which has a liquid surface elevation of 10 feet, got 150 psi-G with a density of -50. And what we're going to do is go through this heat exchanger. Now, let's take a look at this pump just briefly. Okay, so we're going to use a pump curve. I've already entered the pump curve. If you wanted to actually see the data for that, you can simply pull it up. Nothing very fancy about this. It's just flow versus head. We've created a curve. And there's our pump graph. Okay, fair enough. And I'm going to cancel out of here, so it's going to go through and it's going to hit a heat exchanger. And in fact, let me move this just to the right a little bit. J5 and J6 are identical, meaning they have exactly the same resistance curve. Okay, so it's the same resistance curve which I've already entered in our thermal data. Well, we'll discover this in a second. Really, what we're going to be doing is varying this. The inlet temperature for the secondary fluid, okay? And the question is, what does that have to be, that temperature, to achieve our certain goal? And again, I'll mention the goal here in just a second. So it's going to go through a couple different heat exchangers, and then it's going to go off to J8. Now, as you'll notice here in the workspace, you'll notice that you have capital and highlighted in red, a V, and that stands for variable. Again, we're going to vary the temperature, the inlet temperature of the heat exchangers to achieve a goal in pipe 8. Now you might ask specifically, what are those variables and what are those goals? Well, if we simply just go up to the analysis menu and hit the Goal Seek and Control Manager, and if I open the spec window, again, what I'm going to find is a couple different things. I'm going to find all my variables, I'll be able to define my goals, and then I'll also be able to tweak the numerical control. Now, I'm not going to talk about this specifically today just for time's sake. But if we look at the first tab, what I've got here, and I'm going to move this over to the right again so we can take a look at this a bit better. I've defined two different types of variables as it relates to J5 and J6, so both of the heat exchangers. I'm going to apply those. Of course, it's a junction type. The junction type's a heat exchanger with those junction numbers. And again, I'm going to be looking at the secondary inlet temperature, and I'm going to link the two, meaning whatever solution I find for J6, the same will be true for J5. That does not have to be the case, by the way. But in this case, I'm forcing commonality. All right. Now, further, if I wanted to define any upper or lower boundaries, I could do so. In this case, it's not necessary. What's the goal? Well, the goal is a point type of a goal. As you'll remember, there's three different types of goals. I'm going to move this, if I can, out of the way so I can look at P8. There's three different types of goals. In this case, I'm going to be doing a point goal. The point goal is on pipe, and the goal parameter is temperature. And as I'll remind you, there's a cornucopia of different types of goal parameters that you could put in for pipes. In this case, I'm putting in temperature where the criteria is that it's equal to 75 degrees Fahrenheit for P8. In fact, it's not just anywhere on P8, it's the outlet or the inlet of J8, if you will. So that's my goal. We've already defined both my variables and my goals. Well, let's go ahead and run this model. Of course, this is the solutions progress window. What you'll notice here is we're converging on a relative tolerance for pressure, mass flow rate, and temperature based on our solutions controlled matrix. Okay, so we're using the Newton-Raphson method for solutions here. And alternatively, if you wanted to use the absolute tolerance, you could. We chose relative in this case. Additionally, it gives you the total number of iterations. Well, what's new when you're using the GSC module is you'll see this fourth line item. And it says the GSC calls the solver. It'll give you the best, the current, and the total number of iterations. So in this case, there was 56 different iterations to find the solution for the variable. What we're doing is we're saving engineers 56 iterations on a very simple model. It gives you more time to engineer, less time to do manual iterations. Okay, so the calculations converge. We can take a look at the output. Well, when you use the GSC module, what you'll see in the output results is two new tabs. The first is the variables, and the second is the goals. Okay, this is under the general section, the very top. Now again, if you look at the goals tab, well, we already know what the goal is. On the outlet of P, it's going to be 75 degrees. On the variables tab, it's going to give you the solution. So the solution for the secondary inlet temperature is now 96.8 degrees Fahrenheit, and it's common between both of them. What that means, again, if I were to go back to the workspace and I open up the spec window and I go to the thermal data tab, I would change this from 113 to the new solution. Okay, so that's the GSC module and the benefit of it. Well, let's keep moving on. Let's look at another system. I wanted to take a look at a different type of a goal. The last one was kind of a point goal. Well, it was just kind of. It actually was a point goal. This time we're going to look at a group goal. Let me find this model. I've already created it before the webinar here. And here it is. And I'm going to increase the size of this a little bit. You know, before I forget, and it's likely that I will, I just wanted to make sure that I told the audience today about training that we have for Fathom and the modules and also Impulse. Now, if I may, bear with me 1 second. If you go to our main website, we offer training classes here in the United States, both in Colorado and in Houston, Texas. And so I just wanted to make sure I mentioned it before I forgot that we do have a training seminar in April, 8 and 9. This is for Fathom, okay? April 9, that's a Monday, Tuesday in Houston, Texas. And then on the 10th, 11th, and 12th, we have training for Impulse. Of course, that's for Waterhammer. That's the Wednesday, Thursday, Friday. That's a 3-day class. Many people attend both, and it's a total of course, 5 days. And that's in Houston, Texas. To learn more about it, you can just hit this information and registration form. It gives you all the details associated with that. Also, we're having a users group in Houston on April the 11th. It's in the evening. And so if you select this, it'll give you more information on that as well. Of course, it's in Houston, Texas, with Plant Design Solutions. They're a channel partner for the Gulf Coast region, and it's at night, so it goes from 6 to 9 p.m. We have some great conversations lined up and presentations. Trey Walters, the president, will be presenting on our development plans for 2013 and 2014. We're also going to have from Fluor a presentation by a couple of individuals on a boiler feed water and steam system for the BP Whitting project. And then we're also going to be talking about surge and stress analysis and the integration of those using Impulse and Caesar from Intergraph. So at any rate, I just want to make sure that I mentioned those. Okay, back to task here. So what we have here, very simple system. I do that for presentation's sake, just so we understand the concepts. And so we're going to be varying J9. Now, I don't know what it is yet. I'd have to look under the control manager to understand the actual the definitions of the variable, but I can see from a glance that I'm going to be varying J9 to achieve some type of a goal. Okay, so let's take a look at what that, both the variables and the goals. Well, I'm going to vary the pressure of J9 to achieve a group type of a goal. Now, let me put this down just a little bit. It's a group max min with a volumetric flow rate has got to be greater or equal to 125 gallons per minute from the spray discharges. Okay, so you may be asking, so the spray discharges, which ones are we talking about? Well, again, this is a group goal. Let's take a look at what the actual group is. And so if I go under here under the edit menu and I look at the manager, I can see that I've got an existing group. There's only one, again, just for presentation's sake. And so I know that the groups in this, the junctions of this group are J1 through J8. So really, if I say, okay, it's J1 through J8, my group is all of these. Matter of fact, if I go back here and I say groups, and if I say select, spray discharges, and say select, it'll select it for me. So I'm going to vary the pressure to achieve a goal for J1 through J8 as a group to achieve at least 125 gallons per minute. And of course, I would think from an intuitive sense, the limiting junctions would be J1 and J8. Well, let's go ahead and run the model. So again, it took just under a second to converge, very simple model, but there were 62 iterations to the GSC solver, and I'm going to view the output. Okay, so for the output, I'm going to take a look at the goal. Of course, it's what we've already defined, 125 gallons per minute, but let's look at the variables. The variable indicates that my pressure has to be 263.1 psi-G. Now, if I were to take a look at the junctions, matter of fact, let's collapse the pipes for just a second, and if I were to look at all the junctions, well, let's just look at the spray discharge junctions. What we're going to see here is, as we suspected, J1 and J8 have the limiting GPM of 125, and the rest are certainly higher than that. So that meets my requirements. There's my, my variable, which has a solution, and here's my goal. So again, that gives you an idea on how to use group goals. All right, let's move on to the second module we're going to be talking about today, and that is the extended time simulation, or the XTS module. Now, before we dive in the software and drill down to some of the key features, let's talk about a few definitions here. Well, you know, we talk about steady state modeling a lot, and we could do that with Fathom. And it answers certainly a lot of design questions, but really it doesn't answer the question, how do systems perform over time? Now, a couple examples. How long does it take to fill a tank? So we can model tanks filling and draining. Another example would be, how does a system perform when a pump starts? Well, what about when it trips or shuts down? Another scenario would be, what is the total pump energy consumption over a particular time when the operating sequence is varied? And so, you know, as a description for the XTS module, really it's a quasi-steady state approximation to time simulation. Really what we're doing is everything that you can solve using just steady state, you could do without the XTS module. You would create different scenarios and you look at different sequences over different times, different levels, and you could manually, if you will, you could study those in sequence. Now, the problem with that, it's so arduous that people don't do it. It's so time-consuming, it's truly not practical. Let's talk about what XTS is not. Really, when we're talking about the intention for XTS, really it's for slow transients. What does that mean? Well, it's applicable to transients occurring slowly enough that inertia, wave speed, communication time, pipe stiffness can be totally ignored. Okay, so what we're not modeling is pressure waves reflecting back and forth, velocity changing as you would deal with some type of a surge. Okay, so to be very clear, water hammer and surge is referred to as like a fast transient. XTS does not model this. Okay, both subjects involve time transients. Well, that's true. You're studying both systems over time, but they utilize a completely different solution methodology. In fact, you know, a lot of times when we're dealing with time transients as it relates to surge, we're talking in milliseconds or tenths of seconds or maybe even seconds, but not minutes and hours, not as systems change and behave over larger durations of time. Usually surge is considered more of a microscopic view rather than macroscopic. And so if you want to be able to model water hammer or surge, it's a different product that we have, and it's called AFT impulse. Transient parameters. Well, for the different junction types, you can model many different parameters. Okay. So for an example, if you wanted to be able to model a pump, you could vary the speed, the flow rate, the head rise, or the control set point. What about a three-way valve? Well, you can vary the position. The same is true for typical valves. You can vary either the K value, the CV value, or the open percentage. A couple different ways on initiating transients. The first is time. Really what that means, it's relative to the actual simulation time. I'll show examples of this. The second is based on event. Now, it's specified relative to some criteria being satisfied, and in fact, to state it further, it will not occur unless the criteria is satisfied. So two different ways of initiating a transient, time and events. Well, quick overview of nomenclature, if I may. What we'll see on the workspace is if you have a junction, in this case a valve, J3, if you see preceding that, a capital T highlighted in red, that means that there's a transient that's defined in the valve. If you see prior to the junction a number sign, it means that there's a transient defined, but currently it's being ignored. Well, let's take a look by way of example. Let's take a look at the valve variable demand model. It's hard to say. And here it is. Okay, so this is a pretty interesting model. Let me give you a quick overview. I'm going to increase the size so we all can see it, okay? All right, what we have here is we're going to be pumping from J1 through two different pumps. Now, initially, this leg is turned off, okay? We'll discuss that here further in a second. But initially, J3 is on, and in fact, if I were to open up J3, we can see it's from a pump curve, okay? So that's the data that I've already entered is through a pump curve. We're going to hit a control valve, J8, and then it goes off and hits a number of different assigned pressures, okay? So J11 through J19, all of which are controlled by valves. Now you can see that J10 does not have a transient associated with that that we're initiating, but J12 does. Let's take a look at that. Now let me move this here and recenter it. So for J12, it's a valve. The loss model is based on a CV value of 10. Okay. if I go to the transient data, we can now study the initiation of the transient is based on an event. Now, what I've done here, the event is actually time-based. I could have, if I had chosen to, selected time. In this case, I just went for single event. And if you look at the different types of events, it's pretty robust. There's a number of different events that you could have associated with a valve. In this case, I chose absolute time. And so when the time is greater to or equal, greater than or equal to 30 seconds, the following data exists. Okay, this is the transient data. So at time is equal to 0, the CV value is 0. All right, so it's off. At time is equal to 1 second, the CV value is going to go to 10 and it'll remain there. Now keep in mind, this will stay, it's event-based, so for 30 seconds, it's going to be completely off, and then it's going to open over the duration of 1 second and will remain there. Now, as you'll notice here under the optional tab, the special condition is that it's closed. So initially it's closed, after 30 seconds it's going to open. Now, I won't study each of these valves, but this opens at 30 seconds as we just described. This opens at 60, 90, and 120 seconds. And therefore we came up with the name variable demand. So we have different demands over different time. Again, this is time simulation, so it's over 120 seconds. Now, I'm going to open up J8 just so we understand what this is. So we have 4 different types of control valves that we can model. We're going to choose the pressure reducing valve, so we're going to dictate the downstream pressure such that it's going to be 45 psia. Okay? Now, of course, the demand is going to change, so this is always going to be 45 psia downstream. As you can appreciate, based on load, we're going to have some other complexities with this system. And so what I've done here is for J5, which is our reserve pump that's initially off, there is a transient associated with this. And again, here's the transient. It's single event based. And so when the valve open percentage is greater than equal to 50%, the following conditions exist, that over the period of 5 seconds, my pump is going to ramp up to 100% speed, and it's going to stay there for the duration of 140 seconds. Okay? So these two are linked. So initially, this system is all off, and so are these. So really, we just have this leg right here initially. Well, let's go ahead and run the model. Now, what you'll notice that's unique about the XTS module in the solutions control window and the progress window here is that, again, we're converging on head and volumetric flow rate on a relative basis, but you also see a transient bar. It just gives you an idea of the time it's going to take to converge on a solution. In this case, it was just under about 7.5 seconds. Let's view the output. Well, as you'll quickly discover when you're using either Fathom with the XTS module or Impulse, data as it's defined in tabular or Excel type format, as you see here, is useful, but not as useful as, say, graphs. And so today we're going to implement some graphs. It's a better way, it's an easier way, I should say, of looking at data as it's represented over time. I've already created a graph set called volumetric flow through both pumps. And I'm going to go ahead and open that. Now what we'll see here is our flow versus time. And the time, of course, goes out to 180 seconds. You'll see junction 3, which is the upper pump, of course, that started out. Now at 30 seconds, that first valve opened. So then the demand was increased. And it stayed that way till the second valve was open. Then the demand again increased. It increased so much so that the second pump then had to become turned on. And so it did so over the duration of 5 seconds, and it remained that way until yet another valve, and then another valve opened, and finally the last valve. And so you can see the actual volumetric flow rate through both pumps in this graph. You can graph any number of different parameters. In this case, I just happen to choose something that represents the flow rates when all the valves happen to open over time. So that's one example of the XCS module. Let's look at another one. Let's look at the oil transfer system. All right, this is a bit different of an example. What we have here is we have a transfer tank, and then we have storage tanks 1, 2, and 3. Now, each of these different junctions, J6, J8, and J10, all have transients. And in fact, they're the same transient. Let's take a look at the first one. All right, so you can see that the loss model is based on a CV value of 10,000, and that the transient is based on a single event, and I'm going to move this just to the right. It's based on a reservoir liquid height, okay? And when that height is greater than or equal to 39 feet for junction 7, which is right here, junction 7 or storage tank 1, then the following data applies. We're going to take a steady state value of CV of 10,000, and over the duration of 1 minute, we're going to close the valve, and it will remain closed through the duration of our simulation. Now, the same is true for these other two valves. Same type of transient, same definition. Let's look at the transient for J2 on the pump. Okay, so we have a pump curve built in, and if I were to take a look at the transient, looks like when the velocity of the pipe, in fact it's P9, so when the velocity of P9 is greater than 4 feet per second, the following data, transient data, applies, where we're going to go from 100% speed down to 85% speed. It'll stay there over the duration of 1 minute to the final duration is 60 minutes. Okay, fair enough. Well, so if we run this model and we study how this system behaves over time, what we're going to do is we're going to take a look at the liquid levels of each of the tanks and how they vary over time when the valve closes. All right, good. So let's take a look at the output. Again, instead of studying some of the numerical data, I think that I prefer to look at the graph results, and in fact, I've already graphed, created a graph set for the liquid height in the reservoirs. So let's open that. And of course, what we can see here is for storage tank 1, 2, and 3, we can see how, well, I did this in cubic feet, but nevertheless, you can see how each of these tanks filled up over time and when the valve started to close. So now I'm able to study the systems over time. And in fact, if I wanted to look at the pump speed, of course we changed that as well. Now, it's not as nearly as excited, but you can see how the pump was 100% speed and then went down as expected to 85% speed and remained there. All right, we're kind of getting low on time, so I'm going to scurry along here. We're going to look at the last module, which is the settling slurry module. I'm telling you, this is taken off worldwide. When we talk about Chile, Argentina, we look at Peru and Australia, up in Canada, folks are using the SSL module like never before because of the mining operations in those locations. It's a real robust way for users to continue using Fathom, add on the SSL module, and be able to have solutions that they did not have before. Quick intro, if I may. Really, we're taking our calculation methods from the slurry transport using the centrifugal pumps, 3rd edition from Wilson. Okay, so that's the book that our equations come from. They have classes down in Augusta, Georgia. Matter of fact, one of our engineers down there right now taking a week-long class on the calculation methods as it relates to settling slurries. And so a couple different applications, as you may be well aware of. It's transporting raw or partially processed ore in mining operations. Okay, dredging. A lot of work is being done with dredging using the SSL module. Moving waste materials or oil sands mining and backfilling. We use this a lot up in Canada. A couple important definitions before we drill down into software is that we deal with different terminology. And so when we define D50, it's the particle diameter for which 50% of the particles are finer. Okay? Really what that means is it's calculated using a mesh grading test where 50% of the particles are retained on the mesh. Same is true for D85. So we're taking a look at these particles and the diameters and the size and the characteristics of those. We're inputting that information into the SSL module to be able to model the system appropriately. And so D85 is where 15% of the particles are retained. Let's talk about velocity. And of course, Vm is the mean velocity of the mixture. Vsm is the maximum value of the velocity over all the concentrations. I'll show a graph representing that in just a second. V50 is the velocity at which 50% of the particles are suspended by the fluid. Well, there's three different methods within the SSL module for calculation, and each have different input requirements. The easiest, of course, would be the minimal. I'll show you this in our systems properties window. The easiest is the minimal, the second is simplified, and the third is detailed. We're going to focus today mostly on the detail, but there's three different methods of calculation. Well, as I talked about a second ago, V sub m, or Vm, and the maximum settling velocities, really it's based on concentration. So if we take a look at this graph, we have the velocity varying on the x-axis. On the y-axis is a component called Im, and I'm not going to get into the calculation what type of a gradient that is, but it's a gradient that's a very significant calculation that we do and so that calculation leads to many other values that are important to us. And so what we have here on the right-hand side is our concentration and how that varies. All right, and so we have clear water, and then we have varying concentration from low to high. Now what we'll see is our stationary deposit zone. All right, and so you can see how this is going to vary based on the actual concentration. And so the maximum value of Vs is Vsm, which would be right here. The bottom line is that we want to stay with velocities higher than this amount in our system. Why? If you go lower based on the concentration, you're going to have settling beds within your system. It's very destructive. It's so costly to get rid of these. Once they begin, it's very hard to remove without certain practices. And so with our software, we're able to model where the most likely place for a settling bed will occur in your system and how to avoid it. So again, I suppose, I don't know if this is intuitive or not to most engineers, but you can see how we can kind of get away with lower velocities when we have higher concentrations of particles. And the reason, of course, is there's momentum within these particles. There's interaction with these particles, and so they hit each other, and they bounce and knock into one another. And so because of that, they stay suspended within the fluid. Pump derating. It's another big advantage of using our module because it's something that's very important to engineers. And so the presence of solids and flow through pumps changes pump performance. It does two things. It reduces the head generated. It also changes the efficiency profile. Now, there's actually more than two different ways of derating pumps available in the SSL module. The first and most common, I suppose, is the Hydraulic Institute. And so they created a standard. They use impeller diameter along with the solid concentration and percentage of fine particles to calculate head reduction. That's one way. The second way is the Warman method. The third way that we actually have is user specified. If there's a value or that you want to enter, that user wants to enter, you can do that as well. Well, let's take a look at a real-world model. All right, so let's go back to the workspace. Quick intro, if I may. So what we have is a sand pit. We're going to be pumping from that. We have 10-inch lines. It goes uphill to J4, which is just a junction, and then out into a receiving pit. Now, I have a couple different models here. Why don't I go ahead and run that just to see what our output results looks like. So it converges very quickly. And really what we're looking at is a number of different important parameters. Now there's head gradients based on the slurry and based on water. I'm not going to, again, define this for you today, but it's a head gradient. And we have the velocity in the system. Of course, there's an incompressible flow, so it's a consistent velocity throughout the system. Here's BSM, okay? And so that varies based on pipe. And we have a ratio of the mean velocity divided by the maximum velocity. So it's a ratio. Really what we're trying to do is avoid margin. And so as you can see here, based on the pipe angle, we have a 30-degree angle for pipe 3. And intuitively, you would think that, boy, particles are going to collect, and if there was a sliding bed or a bed development, it would be related to that pipe. And sure enough, it is. And we see a ratio of 1.587. Really what we're trying to do is keep that margin above that. It's probably not a safety margin for most engineers. And so I would leave that expertise up to the engineer, but nevertheless you can study this ratio as an indicator. You can also look at any number of parameters. These are configurable in the output control. You can display whatever information is important to you. Okay? And so if I wanted to take some action, if that made me nervous and I believe that there could be the potential of a bed developing, there's a couple different things that I could do, of course. One is I could reduce the diameter of the pipe. The second is I could speed up the velocity of the particles in the carrier fluid. But let's take a look at this. If I went in, well, this is 10-inch pipes. I think the one before, I'm going to load that very quickly. Yeah, the one before was 12-inch pipes. So initially I was at 12. I went down to 10 to speed up the carrier fluid and the particles to such that there would not be any settling. But let's take a look at the actual derating of the pump rather. So if I were to open up the pump properties window, and again I have a fixed volumetric flow rate of 5,000 gallons per minute. But if I take a look at the slurry derating for the pump, again there's 4 different ways. Well, the first is not, let's ignore it, we're not going to worry about the derating. The second is the HI method that I described. The third is the worm, and the fourth is the user defined. But in this case I'm going to use the HI method. I then have to enter the percent fines for the head derating data, and also I have to specify the impeller size, which in this case is 26 inches. Now in our calculation methods, the efficiency is the same as the head derating. Okay? Now, if that's not the case for your system, or if you want to enter a user-specified derating factor, you could alternatively select that. All right, so let's run this model. I'm going to view the output, and in the general section, what we'll see here is under the pump summary. Now what we're seeing is 2 different figures. This is the correction factor based on efficiency and based on head. Now again, as I said before, these are going to be the same value. And you would take this 0.95 and you'd use that as a correction for 2 different items. One is, of course, efficiency, and the other is for overall horsepower. So we're looking at horsepower and we're looking at head. So instead of 123.7, it's going to be that divided by the efficiency factor of 0.95. And so it corrects for both the head and the power. All right, I need to wrap up here. We're a little bit past our time, but if I can conclude very quickly that the GSC module eliminates the iterative process of determining input values that yield a desired output. Also maximizes the user's modeling efficiency. The XTS module. Well, now with the XTS module, we can now study the behavior of systems over time. A couple examples. Pumps starting or stopping. If there's any speed variations within your system. Could be valve position changes or control valve set point variations. We can certainly model tanks filling or draining. Of course, with the SSL module, we can look at how your system behaves with transporting different types of particles, different sizes of particles. We can calculate settling velocities based on different concentrations. We can also study the pump derating, which of course is the effects due to the solids present in the system. For the Q&A, I tell you what, we're going to pass on that. I want to be respectful of everybody's time. And we're going to go right to the end here. So the completion of the webinar, well, what to expect next? Certainly we're going to be sending out a follow-up email. It'll have a link to today's recorded webinar. We'll list the additional webinars that are upcoming here in the next number of weeks. We want to take a look at the software and study some of these modules that we talked about. Feel free to download a demo from our website. It's AFT.com. There's no cost to that. And it gives you an opportunity to play around with the software and get a feel of the ease of use and the capability of the software. If you'd prefer to have an evaluation license, that's a time-limited actual license of our software, feel free to request that by emailing me. It's jeff.warren@aft.com. Common question for pricing. Well, for the United States, we post on our website. You can go there and check out our pricing. For international pricing, please see our channel partner. That's on our website. You just contact the channel partner that's closest to you. I want to thank everyone very much for your time. I hope it was valuable to you. Have a great day.